Electric intensity due to a spherical shell. Charge is distributed over the surface of a hollow sphere. Electric field lines originate from the surface radially outward. A spherical shell of radius r with its center O, and it is charged with a charge density sigma coulomb per meter square. Charge of the sphere is equal to charge density into volume of the sphere, that is Q is equal to sigma into 4 pi r square. Find the electric field intensity at any point outside the sphere. Consider a point P at a distance r from the center of the sphere, where electric field intensity is to be found. Imagine a Gaussian spherical surface of radius r with its center at O, including the point P. Since the electric field lines originate normally from the spherical surface, the electric field lines are also normal to the Gaussian surface. Since the electric field lines are normal to the Gaussian surface, total flux through the Gaussian surface is equal to closed integral E dot ds is equal to closed integral E ds is equal to E closed integral ds. Closed integral ds is the total surface area of the Gaussian surface, that is E into 4 pi r square. The total charge enclosed by this Gaussian surface. Since the charge sphere is inside this Gaussian surface, the total charge in the sphere is the net charge enclosed by the Gaussian surface, that is equal to Q. By the Gauss's theorem, the total flux through this Gaussian surface is equal to 1 by epsilon 0 Q. The two equations you know now of total flux through the Gaussian surface. According to the Gauss's theorem, I is equal to 1 by epsilon 0 Q. I is equal to E into 4 pi r square. Another equation you derived. E into 4 pi r square is equal to 1 by epsilon 0 Q. E is equal to 1 by 4 pi r square epsilon 0 Q. Now rearrange the equation. We can write E is equal to 1 by 4 pi epsilon 0 Q by r square. This equation, the distance in the denominator is r square. This r is the distance from the center to the surface of the Gaussian surface. So the equation shows that even though the charge is uniformly distributed over the surface of the sphere, it behaves as if the whole charge is concentrated at the center of the sphere. So surface charge density, the equation becomes E is equal to 1 by 4 pi epsilon 0 Instead of Q, we can write 4 pi r squared sigma divided by r square. 4 pi in the denominator and numerator cancelled, and in terms of surface charge density, the equation becomes E is equal to sigma by epsilon 0 into r square by r square. P is inside the spherical conductor. The Gaussian surface is inside this sphere. So the Gaussian surface does not contain any charge. The electric field intensity inside the charged shell is 0. How electric field intensity vary with the distance from the center of the spherical shell. According to the equation, E is equal to 1 by 4 pi epsilon 0 q by r square. When the point P is inside the shell, as you already studied, the Gaussian surface is considered inside the shell. So no charge is enclosed by the Gaussian surface. E is equal to 0. When the point P is on the surface of the shell, R becomes capital R, the radius of the sphere. E is equal to 1 by 4 pi epsilon 0 q by r square. The value is maximum. When the point P is outside the shell, E is equal to 1 by 4 pi epsilon 0 q by r square. As the distance increases, the electric field decreases. So it can be represented graphically as shown in the diagram. Up to this distance, up to the distance R, no electric field. On the surface it is maximum. Then it decreases inversely proportional to the order of inversely proportional to r square.